Welcome. In this video, we're going to discuss exponential regression. In Unit 1, we discussed linear regression, and if you remember, that is basically connecting these dots that aren't really connectable with a line. That's what we did with linear regression. So now, rather than connecting them with a straight line, we're going to look at exponential models that might be a better fit. Before that, let's warm up. So we're going to start off by filling in this table in front of us, and I'm going to do the first 3 rows, and I will leave the last 3 rows as an exercise on Canvas. First row, f of x equals 4 times 1.03 to the x power. Our initial value is this number here, so that's the 4. Growth or decay. So remember, to figure out growth or decay, look inside the parentheses. If it's larger than 1, then we know it's growth. So I'm going to put a G here. Now, what is the growth or decay factor? That is 1.03. Now, the growth or decay is a percentage. We want to find the difference from 1. This is larger than 1, and the difference is 0.3, so that is a percentage is 3%. What about G? G of t equals 10 times 0.98 to the t power. Our initial value is 10. Now here, 0.98, it is between 0 and 1. So it's less than 1. That tells me it's decay. The growth or decay factor is 0.98. We're looking for the difference above or below 1. This one here is 0.03 above 1, which becomes 3%. This one is 0.02 below 1, so that's 2%. All right, row 3, and row 3 doesn't give us very much. In fact, we are not even given a function. I'm going to start by just calling it, say, h of x, and I'll start there. I know its initial value here is 1,000, so I can write 1,000. I know I'm going to have an exponential function, so I'm going to leave an open parenthesis. And then here I'm given a really big clue. I'm given that the growth or decay factor is 1.05. And finally, I need my exponent to the x power. Now this is definitely growth since 1.05 is larger than 1, and the growth or decay rate is a percentage, is 5%. And let me do one more. I'm not going to do the 4th row, but I will do the 5th row because it's a little bit different. Actually, no, let me do the last row. Let's do this decay one here. I'm going to call this m of x. I'm told my initial value is 200 from the table. I'm told it's a decay. So I know I'm going to have 0 point something. But what am I going to have? Well, as a percentage, the decay is 49%. That means we're 49% below the whole. So 0.9 below 1. That gives me 0.51. So the decay factor is 0.51, which goes here to the x power. These two will be on Canvas as a graded exercise. Revenues from the sale of compact computers are shown in the following table, where T represents the time in years since 1990. That means 1990 is represented by 0. It is not represented by 1990. It is not represented by 90. It is simply represented by 0. 1992 is here, 94 and 95. And then R is the revenue in billions of dollars, so 3 billion, 12 billion, 50 billion, 90 billion. We're going to find a linear regression and an exponential regression model for the data. So for this example, I'm going to use a TI calculator. We want to start by tapping our stat menu. And once we're there, you want to hit edit. And then your time in years since 1990, this is the independent variable. Revenue is the dependent variable. So we're going to start by typing in time in the first column in L1. So I'm going to pop in a 0, enter, 2, enter, 4, enter, 5, enter. And in the next column, I'm going to type in the dependent variable, that is the revenue. So 3, enter, 12, 50, and 90. And now that that is done, I'm going to quit. So second button and quit. And once here, let's go ahead and go back to our stat menu. And now we're going to go over to calculate. So you're going to want to arrow over. And you're going to want to go to number 4, lin reg ax plus b. Our independent variable is x here. So these are the x's, so to speak, in calculator notation, and these are the y's. That's L1 for x, L2 for y. We're going to store our regression equation by hitting vars. Then we're going to scroll over to the right for y vars, hit enter for function and y1. Then we're going to go down and calculate. And there is our linear regression equation. I'm going to take a moment to write that down. And as you can see, I rounded to 4 decimal places. So that's the linear model. Now let's go ahead and compute an exponential model. So here's the calculator again, and I'm quitting by hitting the second button and quit. Now back to the stat menu, over to calc, and then I'm just going to tap downward until I find exp reg. That's exponential regression, and I just passed it. So here we go. Enter. So L1 is our independent variable, L2 is our dependent variable, and I'm going to go ahead and store this again. Go to vars, function, y vars, function, and then store it in the second one by hitting 2. Enter. And there is my exponential regression equation, and let me write that down as well. And there we have both our linear and exponential models. If you happen to get out of your calculator by accident before you write them down, the benefit of storing them is now I can go to y equals, and under y1 I have my linear model, under y2 I have my exponential model. Part B, let's fill in the table of predicted revenue values using the 2 regression equations. So you'll be very glad that you have these entered under y1 and y2 now. Since you can just go here to table by hitting the second button, then the graph button, that'll activate the blue little table there. And this is my linear model, and this is my exponential model. So for x equals 0, and actually let me label these in the same color. So linear, we have red, and an exponential one is blue on the calculator in front of you. So for the linear model, when x equals 0, y, that is the predicted revenue, is negative 7.441. The exponential predicted revenue is 3.0351. So take a moment and fill all of these out. Now that we've used technology to fill in our table, which equation is the better model for predicting revenues? Why is that? Well, let's look at our graphs for a better picture. Let's take a look at our graph. So go to your stat menu by hitting second and stat plot. We want to turn our stat plot on. Hit enter, and then let's turn it on, and we want these dots. And we already have something blue that's going to show up, so I'm going to change this to green. And definitely not red, because we have red. Let's see, there it is, green. Perfect. Now that we've turned on our stat plot and given it an appropriate color choice, let's go to our graph. As you can see, we're not really seeing much. So let's fix our window. We really want to see maybe x from 0 or a little before 0, a little bit past 6. So let's fix that. I'm going to go my x minimum as -2. I'm going to have a max of 7. And my scale, I think I will stick to 1 for the x window. Now for the vertical axis, I really don't want to go that far negative. So let's go, actually wait a minute. Now that I think about it, our predicted revenue in the linear model is -7. So let's actually stick to -10 here. And for positive, the largest number we have on the positive y is 94, so I'm going to go to 100. I'm going to have the increments by 10. And now let's graph. That is much better. We see all of our points. And we can easily see both the linear model in red and the exponential model in blue. So now, with this picture in mind, which equation is a better model for predicting revenue? If you said the exponential model, you're correct, and I'm not going to write anything down in this space, so please write this down in your own words. The exponential model is clearly a better model. As we can see here, it comes closest to reaching all of these points, where the linear model is pretty off. And in fact, the linear model predicted that the company is at a loss by over $7 billion in 1990, whereas the exponential model is a lot closer to the actual revenue in 1990, which, if you recall, is $3 billion, and the exponential model here predicted about $3.0351 billion. So definitely the exponential model is better. I hope you have something written down in your own words.